Hello students, so welcome to the lecture where we were discussing the structural study of proteins using absorption spectroscopy. So, we are familiar that there are some chromophore in protein, basically intrinsic one, and some prosthetic group like tyrosine, tryptophan, phenylalanine. Tryptophan is the most dominant one, followed by tyrosine, and phenylalanine also contributes little bit, and then disulfide bonds contribute. We also looked at how to understand the protein stability using absorption spectroscopy, and we looked at any temperature there will be equilibrium between folded state and unfolded state. At lower temperatures, so such as 4 degree or even 10 degree, more folded, less unfolded for any stable protein, and as we go keep increasing 25 some unfolded state, 37 significant unstable state, at 50 or 70 completely unfolded state, a very low fraction of folded state will exist. So, that means any temperature there will be equilibrium, and at a temperature where 50% is folded, 50% is unfolded, that is called Tm. So, we are looking at that. Now, let us extend our discussion on the melting temperature, that Tm, and stability determination of any protein. And this is very important, right. So, important in terms of that many organism essentially has optimized this Tm for their survival, right. So, let us see if Tm value is less than 45 degree, right. So, organism, it is a cold adapted organism, they are called psychrophilic. It is a low stability protein, and like a arctic fish have those proteins which have less Tm. Now, 45 to 55, these organisms will be called mesophilic or common mammalian. We have our protein which are in this range. It is a moderate stability, like our protein, like a BSA, bovine serum albumin, or IgG, immunoglobulin. These are the proteins. Like the thermophilic, the heat tolerant organism, thermophilic organism, their Tm will be in the range of 55 to 70, the high temperature. It is a thymus protein. 70 to 85, the thermophilic, the heat resistance organism, it is a very high stability archaeal protein. Then 85, it is a hyperthermophilic, extreme stability, and the stability of protein is extreme. Deep sea vent proteins are of those nature. So, right. So, you see what is the use of such understanding. See, if your protein is here, right, our protein, and you want to make it more stable, what you need to do? Learn what is the similar kind of protein in this or this organism, thermophilic organism. Can we mutate something by protein engineering, so that the protein that we want to make it stable behaves somewhere here? Though it is protein from human origin, but by mutating few residue, that sequence alignment you have to do and do the mutation, protein becomes more stable. So, simple concept of that, one can use it and make a protein, engineer protein which is very high stable. What is the clinical relevance of such understanding? So, say we know there is a mutation, all the time mutation exists in any organism or any protein or something like that. There can be a mutation which will be a stabilizing mutation, destabilizing mutation, or neutral. So, suppose a mutation is happening which destabilizes the protein, what it will do? It will reduce the melting temperature by 5 or 20 degree. In case of cystic fibrosis, that is what happens, and because of that it is a loss of hydrophobic interaction happens, and protein gets destabilized because of this mutation. The another possibility is a neutral mutation, the Tm does not change, like a polymorphic or silent mutation that happens, and it is a compensatory interaction, means one amino acid is changed with another amino acid, but stability has not changed, that is we are calling it the compensatory interaction. Then mutation can happen which will stabilize, that means it increases the Tm by 5 to 10 degree, prion protein, right, prion protein. The increased stability promotes the aggregation. Now, protein goes, if you remember the folding funnel from other courses, protein are stable at there, but when they form ambloids, the folding funnel energy comes at this position. So, it stabilizes the protein, right. Now, predicting the stability of at different temperature one can do by using again concepts of Van 't Hoff equation. So, 4 degree as we had discussed, it is a storage temperature, refrigeration, delta G is more positive, it is stable. 25 room temperature storage, delta G is positive, but it is decreasing. 37 the physiological or human body temperature, delta G is lower, stability is challenged. At 50 degree, it is a fever condition, delta G is near 0, significant unfolding had happened. At 70 degree, cooking condition, delta G is negative and it is a complete unfolding that has happened, right. So, one can use this simple concept of thermodynamics associated with absorption to understand the stability of a protein. So, let us look at now other condition, that was heat condition. This condition is chemical denaturation. So, you know the protein can be chemically denatured by adding some compound like urea or guanidinium hydrochloride, which denatures the protein. So, one can use this for understanding the protein stability by delta G extraction. So, denaturation equilibrium, the denaturation titration one can do and find it out stability determination. So, what we are going to do is take the protein, add little bit of urea and keep increasing it, and as the urea increases, protein gets unfolded and its absorption and all those will change, like something like this. You see here the absorption we are measuring, here increasing the urea concentration. So, as you increase it, here the absorption decreasing and then again it is increasing. So, this is say unfolding happening and then protein gets precipitated, aggregated and all those, and Cm is the midpoint where 50% folded, 50% unfolded happened. So, if you plot that fraction unfolding, so here one can see that it is in the folded state regime, here transition is happening and at this point here 50% folded, 50% unfolded, this is the unfolded state, and one can calculate the delta G of unfolding upon denaturation condition, right. So, this is the experiment, we are creating the denaturation series 0 molar to 8 molar at 25 degree, we are measuring the absorption after 24. So, it is a equilibrium experiment, we are making 8, 10, 12 samples. Between 0 to 8 molar of urea, we added equal amount of protein to that, we incubated for 24 hours, measured the absorption and from there we are calculating the fraction unfolding by this formula. Absorption at any concentration at 280, absorption at 280 native condition divided by absorption at unfolded state and minus absorption at native. So, that gives this Cm, that is a midpoint, 50% is in folded state, 50% is in the unfolded state. So, for lysozymes, suppose lysozyme 50 kDa protein, right. So, lysozyme Cm is 4 molar urea, it is a good stable, you can use that as a standard reference. BSS 66 kilodalton, it is again Cm is 3.5, it is a moderate, it is a variable batch dependent, and IgG immunoglobulin is 3.8 Cm, it is a good stable, and this is one of the protein that is used as a therapeutics antibody, it is a stable one, right. So, one can do this urea denaturation and extract the delta G. So, urea one has to do it 0 to 8, other one can be guanidinium hydrochloride 0 to 6 molar, acetamiide 0 to 6 molar, SDS one can use 0 to 200 millimolar or acid base 2 to 12 pH, you can change it. Now, one can have a pKa property of each of these, and mechanism is that what urea does, basically it direct solvation of polar group it does, guanidinium direct solvation and also ionic effect because GD and HCl. Now, acetamide direct solvation, then SDS puts negative charge on the protein, so that is a surface denaturation, and acid base basically it breaks the charge interaction, that is a charge disruption. So, you remember when we run SDS page, we add like a high concentration of SDS to denature the protein and put the uniform negative charge. Urea denaturation is reversible quite a bit, guanidinium is also reversible, that means you remove that guanidinium, protein can come to native state. The acetamide is reversible, SDS is partially reversible and acid base depends upon how much you have denatured. So, the mechanism of chemical denaturation, like as we mentioned, urea interacts preferentially with the backbone of a protein, that is CO and NH, because you remember what is the structure of urea, CO NH2, yeah, that is what, no, CO NH2. Now, this has oxygen group as well as NH2 group. Now, that can here compete with the backbone of the protein and can make the hydrogen bond, and then the hydrogen bond which exists in the protein can be broken, and now because of that denaturation starts to happen. So, that is what it does. Now, again it disrupts the hydrogen bond by stabilizing the native state of protein and hydrophobic. Now, urea can create an environment where hydrophobic side chain can be solvated in non-polar environment like urea, and then the interactions are broken and it denatures. Now, indirect solvation, how it does? Basically denatures, denaturant decreases the water activity and protein hydrates as a compensation. So, that is what happens. Now, that was urea dependent. We can have a pH dependent stability of ionized group. So, acid base denaturation one can have effect of ionization on protein. So, if you look at, as we had discussed few minutes back or the previous class, tyrosine has a pK of around 10 and pK range for stable is 8 to 13. Effect of ionization, it can destabilize, right. So, spectroscopy signature what comes? It shifts the lambda max. So, 274 is for normal, when it get ionized it goes to 293. Similarly, lysozyme, its a pK is about 10.5, the range is 9 to 11 for destabilization. Here the loss of charge, because you remember lysine has a positive charge at the site. So, if you keep increasing negative charge, stabilization will be lost and it will be destabilized. Similarly, arginine, again positive charge, increasing the pH will destabilize it. The cysteine, its a pK model is 8 to 9, range is 7 to 10. This thiolite formation happens and 280 increases, the absorption increases weakly. The spartate and glutamate, these are negatively charged amino acids. So, its range is 3 to 6 and protonation reduces the charge, and that is what it happens. So, tyrosine at 8 neutral, 10 transitioning and 12 it is ionized, and that is what lambda max shift happens. So, one can look at the protein stability by doing this pH dependent titration and find it out at what pH it is optimally stable. So, at lower pH it is not, at say optimum pH for this will be 5 to 7 and then destabilizes it. So, looking at the absorption of tyrosine residue, you can find what is the optimum pH where it can be stabilized. So, stability versus pH relationship, one can have like 2 to 4 pH it decreases, 4 to 7 it is a maximum, 7 to 10 gradual decrease, 10 to 12 rapid decrease and 12 after 12 it is a strongly negative. The group that are there negatively charged in this range, this is the native state. Here most ionized state, tyrosine ionization happens in 10 to 12 and mostly ionized protein. So, in this range acid denaturation, 4 to 7 optimal stability, 7 to 10 slightly destabilization, then 10 to 12 progressive unfolding and beyond 12 it is a completely denatured. So, what it says that this is the range where your protein is most happy, 4 to 7. So, temperature you have to keep low temperature, pH you have to keep 4 to 7 for your protein to be stable. So, clinical example storage of pH where we are going to use this. So, if you look at immunoglobulin, which is the antibody, therapeutics antibody, optimal pH for this guy is 7.4. Tm for this is 73 like at optimal pH, and if you decrease the pH its Tm decreases 55, at 12 it is 48. The insulin So, optimal pH, if we are at 7.4, this protein is stable up to 73 degrees. So, that is the best pH for immunoglobulin. If you look at insulin, it is a 51 amino acid, approximately 6 kDa protein. Optimal pH is 2 to 8, right. It is also stable up to 70 degree, and as you decrease the pH, it slightly increases. If you increase it, it goes up to 45 degree. The BSA optimal pH is 7.4, say 67, if you increase or decrease, it decreases. So, that means in this range, if we are putting the protein, the stability of protein is good. So, that means maintain the physiological pH of pH 7.4 for most of the therapeutics protein to stabilize the stability and shelf life. So, proteins should be stored at say temperature 2 to 8, and formulation should be between this range, right, as around physiological pH. That is why your protein is more happy and can be used. Now, therapeutic protein quality control, right. So, when we are making a drug, it is important to ensure that it is of highest quality. Therefore, quality control becomes extremely important, because these drugs are going to be injected in the human body, and any deviation in the protein structure can cause havoc. So, therefore, quality assurance and quality control, QA and QC, are very important, and that can be monitored by UV visible. So, one can monitor something called critical quality attributes, which ensures the quality of a therapeutic antibody. So, MABs, as we know, fastest growing class of therapeutics. Over the hundreds FDA approved MAB drugs are in market, and rigorous quality control is required for any analytical technique to ensure the product safety, efficacy and consistency. Right. So, how CQA can be done for a therapeutics antibody? So, CQA parameter, the protein concentration, monomer purity, aggregate content, thermal stability, disulfide and change in the heterogeneity. These are the CQA parameter. So, let us take one by one. If we are ensuring the protein concentration, you can use 280 Beard-Lambert law. The normal range one can have 1 to 50 milligram, and clinical relevance, this is accurate dosing, batch consistency, and analytical window that we are going to have 0.1 to 2 analytical window for measuring the concentration of a protein. Monomer purity, you can use monomer, right. So, not only your UV visible will do, you have to invoke other technique like size exclusion chromatography. So, measure the concentration at 280, include that with a size exclusion chromatography to find it out. What is the normal range? You have to have as much monomer percentage is, that is a 95% monomeric. So, it ensures the efficacy, safety and immunogenicity, right. It is a quantitative. The aggregate, very dangerous species, you can measure it by absorption at 350, which is not absorption, but a scattering, and you can measure up to less than 5% aggregate. This has a huge immunogenic response, and up to 0.1 AU is the analytical window. Thermal stability, you have to, because storage, freeze, thaw, many things comes into thermal stability, right. So, thermal stability one can measure at the TM. The normal range is 70 to 75. It is critical for storage condition and shelf life. The change analytical window is 0.1 to 1 unit. The disulfide, that ensures the critical quality attributes. So, if you remember the insulin structure, there are 3 disulfide bonds. You have to find that they are correctly formed. So, AAT after reduction, and normal is like a structure is conserved or not, it is used for structural integrity, it is a comparative. The charge heterogeneity, pH dependent charge at 280, the minor variation happens, and the functional form distribution one can find it out, and a spectral shift gives idea. So, monomer versus dimer detection, as I was mentioning, you have to club your UV visible with size exclusion chromatography, and in size exclusion also what we are doing, detecting using UV visible. So, there is a column through which samples are purified and you detect using UV visible. So, here you get a suppose a profile like this, elution profile, monomer and dimer, right. So, you can look area under curve and we can quantify how much percentage is monomer, how much percentage is dimer, and if there is another species even bigger aggregates, you can find it out. So, acceptance criteria is more than 95% of monomer should be there in the product, then only you can take it, right. So, how we do quality control test for every batch, because batch to batch you have to ensure, and you cannot invoke a very hi-fi technique for that. You require a simple technique which can do the batch to batch analysis for monoclonal antibody. So, you measure the concentration using Beer-Lambert law. Equipments you require is UV visible, concentration you get mg per ml concentration less than 5 minutes and it costs less than $20 for getting it. The purity you can get it like whether DNA contamination is there or not, 260 by 280 ratio. One can do using UV visible spectroscopy less than 5 minutes. The monomer purity you can do with SEC HPLC plus absorbing at 280, SEC is size exclusion chromatography, high performance liquid chromatography. You require HPLC system or the ECTA-pure kind of system, FPLC system. You get a monomer, it requires 30 minutes, cost is slightly higher. When we are going to do aggregate analysis, you can do dynamic light scattering or the scattering simple using UV visible. Here you require zeta sizer or spec, the percentage of aggregate you can find in 10 to 15 minutes. Now, the another important parameter is endotoxin. So, you have to do some other assay, LAL assay, right, with the so you are putting any toxin are present in the monoclonal antibody or not, that also you can get the titer and find it out in $100. The sterility of the culture media where protein is getting produced, that can even pass or fail by looking at what kind of culture media we are using. And finally, comes whether the drug is potent or not. So, you have to do bioassay, that means binding to the receptor analysis, that can be done by ELISA and pediatric reader. This also takes some money. So, these are some of the routine quality control test you can do for therapeutics antibody, and you can do total release testing in 1 to 2 days in $1000 or something per batch. But forget this money, it is extremely important because you are going to inject the same drug in one's body. So, it has to be highly pure and highly confident that this is a good protein, right. So, not only that, we can use this simple concept in biomarker quantitation and point of care diagnostic, right. So, how are we going to do? Say protein that are there in different disease which can be used as a biomarker. The myocardial infarction, the protein which is used is troponin 1, cardiac troponin 1. The normal concentration is less than 0.04 nanogram per ml, and elevated level can be 0.5 nanogram per ml. The Tm for this protein is 68 and diagnostic window you have to do it in 24 hours. So, you can measure the concentration of this protein and find it out whether this has increased or not. Simply prostate cancer, you can have a prostate specific that can be detected. In normal case, it is a less than 4 nanogram per ml. In the prostate cancer case, it is 20 nanogram. The Alzheimer's disease, phosphorylated tau, one can detect it, again it is a low, in disease case it is very high, Tm is 60 degree, you can be using for preclinical or clinical application. Similarly, CKD, chronic kidney disease, creatinine level goes up, which is typically measured, and this is again it is a monitoring can be done continuously when dialysis or some person is coming. You can measure the creatinine level by UV visual spectroscopy. The liver disease, the alkaline transaminase ATL level can be measured, right. Then COVID-19, it was also used spike protein, how much spike protein is there, and normal it should be negative. In case of COVID infection, it increases, and that is for acute infection. The tuberculosis, the LAM, right. So, LAM can be measured, in normal case it should be negative, in the infected case it should be positive. So, active TB diagnostic can be used, right. So, all these protein biomarkers using UV visible you can find it out whether they are present or not. So, and one can get it the diagnostic test using the simple concept. Right. So, enzyme linked immunosorbent assay, that gold standard one can do. It is a simple 5-step process. Sample plus antibody coated plate you take, then add the detection antibody, then like a HRP conjugate, then add the substrate that is colorless. If binds, it gives you blue color and you quantify it. So, in 96 well plate you can basically take it, standard plus 360 well high throughput one can do, room temperature one can do, and you get the PSA concentration, right, PSA concentration with absorbance at 480 and assay time is 2 to 4 degree with a 96 well plate. So, one can basically detect it enzyme link ELISA kind of assay for these. Now, as I mentioned here, so for infraction, myocardial infection, troponin C can be used. So, say what we are doing clinical scenario, patient present to emergency with a chest pain, right. So, you have to find it out what is happening to that guy. So, rapid troponin test can be done to determine if it is a myocardial infraction or not. Typically what you have to do, sandwich ELISA you have to do, capture and detection antibody you require, detection range you can do 0.01 to 5 nanogram, it is a highly sensitive. Sample you just require 10 microliter of serum sample, then time 1 hour, in 1 hour you are going to do the wavelength, you are detecting blue and positive cutoff. So, here you can see here diagnostic cutoff is up to this, and low concentration no myocardial infection, if high concentration it has happened. So, like if you just look at in 6 hour, if this is case discharge and output stress test, if this is happening septic myocardiopathy, critical care you have to send it in sepsis case or in a stable angina case. So, just by measuring the concentration of troponin protein, one can find it out and quickly provide the observation what is happening to the person. Similarly, you can use this concept in point of care testing microfluidics device. One can make it just flowing the sample like in any laboratory, you can do it bedside also and make a microfluidics device. Just you see the lateral flow strip test assay and make a continuous monitoring device or lateral flow assay with a cheaper cost and find it out whether it is happening or not. Simple like a COVID-19 test, one can do the test like other things, one can basically do it to capture whether the disease burden is there or not, like a rapid, like you remember during the COVID pandemic, the COVID-19 rapid antigen test was happening, and basically just by colorimetric test people are saying if there is a visible line, if negative, control, a visible line if positive, antigen is positive. So, lateral flow assay, basically you are taking that nasal swab and putting it in solution and putting in a lateral flow assay. By looking at the lines, you are saying whether somebody is positive or not positive. So, that is very cheap and high throughput detection device that can be used for detecting it. Similarly, digital ELISA can be done, it is a high sensitive and rare biomarker one can have. So, traditional ELISA detects about 10 to the power -12 picomolar, but digital ELISA can go up to femtomolar. So, 1000 times more sensitive, essentially like somebody suffering from Alzheimer's. So, you can detect the phosphorylated tau or amyloid beta, that is a very low concentration, and digital ELISA you can put it and detect even the femtomolar concentration of a protein as a probably as early biomarker of tau to find it out if some person having the burden of phosphorylated tau or a beta or not, even in the picogram concentration, right, and that basically tells you about what is the condition. So, if this is there, you can track the disease progression, how much tau or amyloid beta is going or not, or where intervention and window is possible or not. So, if somebody is in this range, just phosphorylated tau start appearing, you can start intervention early and probably you can have you can provide a better life or lifestyle management of a people who are suffering from Alzheimer's or so. So, just to sum up, this simple technique has a tremendous application and one can use this concept to make a sensitive device like a microfluidics device we discussed, the ELISA based device we discussed, this digital ELISA or lateral flow assay, and one can have the early detection or a faster detection. You can deploy this in bench side like a bench side research to bedside for early detection. So, understanding these concepts becomes very crucial and opens the window or avenue of what is the possibility that can be explored understanding the UV visible spectroscopy. So, with this let us stop it here and we look forward to you in the next class, and if you are like interested to understand many of these already I have discussed, the therapeutic antibody, the clinical biomarkers what we can do. So, if you are interested to read more, these are some of the reference paper, you can go it and read more and get yourself acquainted with what is happening in this field. So, thank you very much and looking forward to have you in the next class. Thank you.